Have you ever stood by a massive dam and just felt the immense power held back by that wall of concrete? It's awe-inspiring, right? But have you ever wondered how we turn that incredible force of water into the electricity that powers our homes, charges our phones, and lights up our entire world? Today, we're going to dive deep into the fascinating world of hydroelectric power plants. We'll uncover the simple yet brilliant engineering that transforms a flowing river into clean, reliable energy. Stick with me, because by the end of this video, you'll see the water around you in a whole new light. So, what's the big idea behind hydropower? At its core, it's all about converting energy from one form to another. Specifically, it's about taking the potential energy of water stored at a high elevation and turning it into kinetic energy as it flows downwards. Then, we capture that kinetic energy and convert it into mechanical energy, and finally, into the electrical energy we use every day. Think of it like a giant natural battery charged by the water cycle itself. Rain and snow fall in the mountains, collect in rivers, and we simply guide that water through a power plant on its journey to the sea. It's an elegant process that humans have been refining for centuries, from ancient water wheels grinding grain to the colossal power stations of today. Let's break down the journey of a single drop of water as it passes through a typical hydroelectric power plant. The story begins at the reservoir. This is the huge body of water held back by the dam. A dam is more than just a wall. It's a carefully engineered structure designed to raise the water level of a river, creating what's called a head. This head is the vertical distance the water will fall. The higher the dam, the greater the head, and the more potential energy is stored in the water. This reservoir acts as our fuel tank, storing water until it's needed to generate electricity. When the demand for electricity rises, the process begins. Large gates, known as intake gates, open up at the base of the dam. Gravity takes over, and the immense pressure from the water above forces it into a large pipe called the penstock. As the water rushes down the penstock, its potential energy is rapidly converted into kinetic energy. It's like going down a water slide, but on a much, much grander scale. The water accelerates, gaining tremendous speed and force as it hurtles towards the heart of the power plant, the turbine. Now, this is where the magic really happens. Imagine a giant, high-tech pinwheel. That's essentially what a turbine is. The high-pressure water, channeled by the penstock, blasts against the blades of the turbine, causing it to spin at an incredibly high speed. This is the crucial step where the kinetic energy of the flowing water is converted into rotational mechanical energy. There are different types of turbines, like the Francis, Kaplan, and Pelton wheels, each designed for specific water pressures and flow rates, but they all operate on this same fundamental principle of using water to create rotation. The spinning turbine is connected by a shaft to the generator, which sits directly above it. This is the final and most important energy conversion. As the turbine spins the shaft spins a series of massive magnets inside the generator. These magnets are surrounded by giant coils of copper wire. According to the principles of electromagnetic induction, a discovery we can thank Michael Faraday for, moving a magnet near a coil of wire creates an electric current. So, as these huge magnets spin, they generate a powerful alternating current, or AC, in the copper coils. And just like that, we have electricity. But the electricity produced by the generator isn't quite ready for our homes yet. It's at a relatively low voltage. So the next step is the transformer. The electricity is sent to a step-up transformer located at the power plant's switchyard. This device increases the voltage dramatically. Why do we do this? Well, transmitting electricity over long distances at high voltage is much more efficient and results in less energy loss. Think of it like increasing the pressure in a hose to send water further. From the transformer, this high-voltage electricity is fed into the national grid, the vast network of transmission lines that crisscross the country. These are the tall metal towers you see stretching across the landscape. The electricity travels along these lines for hundreds of miles, heading towards cities, towns, and industrial areas. When it gets close to its destination, it goes through a series of step-down transformers at local substations, which lower the voltage to a safer level for use in our homes and businesses. Finally, it travels through the local distribution lines, right to the outlets in your wall. And what about the water that did all this work? After it passes through the turbine, its job is done. It has lost most of its energy, so it flows out of the power plant through a channel called the tail race and calmly rejoins the river on the other side of the dam, continuing its natural journey downstream. The whole process is continuous, clean, and remarkably efficient. As long as the river flows, the power plant can generate electricity. One of the biggest advantages of hydroelectric power is its incredible responsiveness. Unlike some other power sources that take a long time to start up, a hydro plant can go from zero to full power in just a few minutes. Operators can open or close the intake gates almost instantly to match the real-time demand for electricity. This makes hydropower perfect for managing the peaks and troughs of daily energy use. When everyone comes home from work and turns on their lights and appliances, hydro plants can quickly ramp up production to meet that surge. So there you have it, the entire journey from a raindrop in a reservoir to the light in your room. A dam creates potential energy, a penstock converts it to kinetic energy, a turbine captures it as mechanical energy, and a generator transforms it into the electrical energy that powers our modern lives. It's a beautiful symphony of physics and engineering, all driven by the simple, powerful, and renewable cycle of water. It's a testament to human ingenuity and our ability to harness the incredible forces of nature in a sustainable way. Thank you so much for joining me on this deep dive into hydroelectric power. I hope you found it as fascinating as I do. If you enjoyed this video and learned something new, please give it a thumbs up and consider subscribing to the channel for more explorations into the amazing world of science and engineering. And don't forget to hit that notification bell so you won't miss our next adventure. Until next time, stay curious.